What I'd like to focus on this video is our domain restrictions. Because at this point, we've now learned all of the critical domain restrictions that we get in basic algebra and pre-calculus. And I would like to summarize those here for your own benefit, and then we will tackle some identifying domains and ranges, well, I guess in this case just domains of some functions. So the first domain restriction, and you should think about this in terms of operations that we give. Most operations that we give in math work really well for all types of numbers, but certain operations have restrictions on them. One operation that has a restriction on it is division, and the rule here is you cannot divide by 0. So the rule is you cannot divide by 0. An example of that might be if I gave you the function f of x is equal to 1 over x, what numbers am I allowed to divide into the number 1? And the answer is I can divide in all numbers except for the number 0. This is not defined for x equal 0 in this case. So the domain here would be from minus infinity to 0, union with 0 to infinity, or I could have written that in set builder notation. So usually these problems get a little bit harder. Instead of just asking you the reciprocal function, what's the domain of that, usually I throw in some transformations or we modify that somehow. So if we're asked the domain of this function right here, the domain of f, we would need to exclude any values for x that would set up this scenario where you would be attempting to divide by 0. So the only problematic operation that I see in this entire expression, you'll notice I'm doing some subtracting by 3, I'm doing some adding by 4, I'm doing some multiplication. I multiply this factor here to this factor here. The only problematic operation in this entire function is the operation of division. And we've got to make sure that we do not divide by 0. So what I'm going to ask you to do when you work these problems is to say we need the denominator not to be 0. In fact, let's just write that. The denominator cannot equal 0. And so there's our denominator, x minus 2 times x plus 4. And so we have that x minus 2 cannot equal 0, so x cannot equal 2. And x plus 4 cannot equal 0, so x cannot equal minus 4. So giving the domain here in set builder notation, it's a set of x such that x can be any real number, except that x cannot equal 2 or negative 4. By the way, we did a whole pre-work looking at the domains of rational functions already in this course. Okay, so then what about other problematic operations? The next problematic operation is taking even indexed roots, e.g., let me just put this down, I'm talking about something like square roots here. Square roots or fourth roots or sixth roots. Remember that here is the radical symbol. We call this the index of the radical. And I'm saying that when the index of the radical is even, we run into a domain issue. Okay? So you cannot take the even root of a negative number. So here we need 2 minus 3x. We need the radicand. In fact, let me just say that. The stuff underneath the radical sign, the radicand must be greater than or equal to 0. So we need 2 minus 3x to be greater than or equal to 0. So we need minus 3x to be greater than or equal to negative 2. Careful here, I'm about to divide both sides of this inequality by a negative 3. When we do that, we invert the direction of the inequality. So negative 2 over negative 3, or x needs to be less than or equal to 2/3. This is probably best listed in interval notation. So the domain of our function g here would be from minus infinity up to 2/3, and because we do allow for x to equal 2/3, we're going to put a bracket here. Notice that if I let x be 2/3 in this problem, we would end up with the fourth root of 2 minus 3 times 2/3. That would simplify to the fourth root of 0, and we can take the fourth root of 0, that is 0. So this operation is defined for when x is equal to 2/3. Okay, then we want to go ahead and look at trig expressions. And here, there's actually nothing new with trig expressions as long as you remember your various reciprocal and quotient identities. So for this, let me just say, recall the quotient and reciprocal identities. and then the fact that you cannot divide by 0. So the issue here with a function like h of x is we probably ought to rewrite it in terms of sine and cosine. I could rewrite this as the sine of x divided by the cosine of x plus 2 times 1 over the sine of x. And what we see here, this is what I mean by using the quotient reciprocal identities. I use the quotient identity on tangent of x. I use the reciprocal identity on cosecant of x. And although there are many other ways to remember these facts, I think this might be one of the easiest, because then we just tie this expression into the original fact that division is a problematic operation. We cannot divide by 0. Okay, so then we would give as the domain anything that would result in we would exclude from the domain, anything that would result in a 0 in the denominator. So in our case, the domain would be the set of x, such that x can be any real number, except that x cannot equal 2n plus 1 pi over 2 and m pi for n and m integers. Okay. Now that's a little bit awkward to write that. Let's just point out that notice that if I let m be any integer, like 3 pi, if m were 3, this would be 3 pi, or if m were minus 2, this would be minus 2 pi, and the sine of 3 pi or the sine of minus 2 pi results in 0, and this entire expression would be undefined because of the 1 divided by sine of x. We cannot allow sine of x to come out to be 0, so we cannot allow the input to that to be some multiple of pi, otherwise this expression is undefined. Likewise, the cosine of x, remember, is 0 at all of the odd multiples of pi over 2. So it's 0, cosine of x is 0 at pi over 2, 3 pi over 2, 5 pi over 2. So we're going to exclude those values from the domain. Because we have the fraction here with the cosine of x as its denominator. So that's why we excluded all of the odd multiples of pi over 2. Otherwise, this expression was undefined. And over here, we excluded all of the multiples of pi. Otherwise, this expression, the second expression, would have been undefined. Okay, all of this is actually a review, these first 1, 2, 3 examples. The new example is logarithms. You can only take the log of positive numbers. So that's our phrase for this one. You can only take the log of positive values. Okay. So careful. Notice I didn't say that x has to be positive here. I didn't say when you're dealing with the logarithms, x has to be positive. I said the expression that you're taking the logarithm of, that's sometimes called the argument, and the argument must be positive. So in this case, our argument is 2 minus 3x, and this must be positive for us to evaluate the logarithm, which means minus 3x must be greater than negative 2, which means that x needs to be less than negative 2 over negative 3, or x needs to be less than 2/3. So our domain here for this last function is going to be from 0 to 2/3 with a soft bracket here, because we can only take the log of positive values. Notice you cannot take the log of 0. So something slightly different here. I think it's really helpful to look at this case and compare and contrast them. Radicals are problematic, specifically when we have even indexed radicals. We require the expression inside the radical, that argument, that radicand, needs to be non-negative. So it needs to be greater than or equal to 0. For logarithms, we can only take the log of a positive number, so the argument needs to be strictly positive. I'm trying to make a distinction here, folks, between this greater than or equal to symbol versus this greater than symbol. And once you follow that out, notice how the two domains here for these two expressions, even though they have similar arguments, 2 minus 3x, the domains are slightly different, and a lot rides on that slight difference. Okay. So folks, this long video finishes out the first part of this, where we reviewed our graphs of the exponential and logarithmic functions, at least for when the base was greater than 1. And then we went ahead and reviewed the idea of the domain and ranges for logarithms. And in the next video, we will look further into doing the domains and ranges of expressions that involve logarithms, but they're going to be slightly more complicated. So I'll see you there. Thanks for your patience, folks. Take care.